Good day. My name is Oiren Kai, and for this engineering dynamic assignment 2, I selected a real-world rigid body system, which is a three-blade stand fan. Now let's see at the video motion. This is the initial state of the fan. The blades are moving, and then the blade stops immediately. For my measurement, I estimate the fan blade radius as approximately 0.2 meters and measure the central hub radius at approximately 0.05 meter. The mass of the fan motor assembly was estimated as 0.5 kilogram and the three blades mass was approximately 0.3 kilogram. To simplify the analysis, I modified the fan as a circular object and calculate its mass moment of inertia using the standard inertia of equation. Next, I analyze the motion using the work energy method. In the step 1, represent the initial condition where the fan is rotating at operating speed. At step 2, represent the moment just before the fan stops, where the rotational velocity decreased due to the mechanical and aerodynamic resistance. Using the work energy equation, I assume there was no external work input after switching off the fan. Therefore, I use the principal conservation of work energy equation, which is T1 plus summation U1 to 2 equals to T2. Since the final kinetic energy becomes zero, the initial rotational kinetic energy is dissipated mainly through friction and air resistance. Then I continue the analysis using the impulse moment method. For step 2 to step 3, the fan experienced a braking effect that generates angular impulse, which is using the formula I omega 1 plus integral m delta theta equals to I omega 2. I estimate the stopping duration as about 0.3 seconds. There are several assumptions were made. Firstly, air resistance was neglected in the theoretical calculation. Secondly, friction was assumed constant, and then the fan structure was treated as a rigid body. After evaluating the result, I found that the theoretical model introduced some limitation. First, neglecting air resistance causes difference between theoretical and actual stopping behavior because in reality, airflow contributes significantly to energy loss. Secondly, assuming constant friction may not fully represent the actual condition because friction changes with the speed and bearing condition. Thirdly, modeling the fan as a perfect circular rigid body simplifies the geometry and may slightly affect the calculated moment of inertia. From the safety perspective, the estimated braking force is relatively small compared with the structural capability of a household stand fan, so the system is considered mechanically safe under normal operation. As an improvement, I propose using lower friction bearing and optimizing blade geometry to reduce energy loss and improve efficiency while minimizing impulsive loading force. That's all. Thank you.